Hey, what's up? So, I am going to make a series of videos about different bases of numbers, right? So, binary, hexadecimal, that kind of stuff. And so, partly that's for programmers, okay? However, in sort of opposition, I don't know, to differentiate myself from a lot of the content that's out there, I'm going to be talking about some more advanced math concepts as well. And, look at that. But I had a question before we get started for all y'all. Are you familiar with this thing called Suica game? This is not it right here. Let me see if I can bring it up. This kind of thing? You see that? Yeah. I've been playing that lately here in Japan, and suika is watermelon in Japanese. So actually, this is kind of related to some of the number theory kind of stuff that I do want to talk about in this series of videos. And I haven't watched this video by Joseph Newton here, but anyway, so my question is, are you familiar with this game? I guess it's called Suica game. I would have guessed watermelon game. But anyway, so I was playing around with some fruity things, and I want to be able to pick things up. And as you can see, it's going great. Things are going great here. But this is going to give people a headache. We got, I kind of threw it. Interesting. We got strawberries, and I think if I push the other buttons, we get other kinds of fruit. So anyway, that's all related. But anyway, there's lots of videos online about, the kind of math that you need for programmers and these different bases. The computer works with ones and zeros. It works with binary. That's what the computer knows. So, well, for most programming, you don't really need to know about binary, okay, really, but just to be a decent programmer in general over the years, there's certain kinds of knowledge that are just useful in general. Like, it's good to kind of know how the computer works in general, right? And so there's a lot of kind of stuff to talk about in regards to that. And I find that stuff very interesting. I hope you do too. Just trying to understand how a computer actually works is interesting. And so binary is important for that. Also, hexadecimal, if you don't know, I'm sure many of you do, but that is base 16. And the reason we often use hexadecimal is that writing out binary numbers or representing numbers in binary is very unwieldy, right? You have these like long ones and zeros. So so if I wrote 101, okay, you're not gonna be able to see that. So let's change to Sublime. I think I have somewhere. Yeah. Here's Sublime. Let me make a new file here real quick. So, anyway, so yeah, like this would be a 4-bit number. You have each bit is a 1 or 0, and so that's 0. So let's start with just explaining what binary is for those who don't know. So I know that a lot of people know what a lot of this stuff is. And the point of this video is actually just an introduction where I'm going to explain what my approach is for this series of videos. And I'll talk about it more later, but the SparkNotes version is basically, I'm going to be talking about higher math concepts also. And my motivation for doing that is that there's already tons of videos out there explaining the basics and the general information that you would want to know. There's tons and tons of that content out there. So I'm going to do something that I'm able to do that's a bit different and relate these higher math concepts that I think are very interesting. And personally, I've been studying some of this stuff not the basics of binary or anything, but I'll explain it probably later. So, but I have reasons for kind of studying different bases of numbers. So I've been doing it personally. So it's just good timing for me. Now, let's talk about what binary is, and because there's probably some people who don't really understand what it is. So binary is base 2. And so our normal number system that you've learned in math is base 10. I'll call that sometimes the decimal system. So ordinary numbers, that's base 10. Now in binary, here's how you count. You start with 0, and then this is 1. And then the number 2 is written like this, 1, 0. Number 3 is like this. Number 4, number 5. So do you see the pattern? We start with 0, we increment, we add a 1. But it's like there's not space to go up, if you will. We can't go up to 2 right here. So we have to put a 0 and then a thing like this. So what happens is, this is the 2's place. You know, like with a normal number, like here's a random number. This is the 1's place. Let me make sure you can see the cursor here. Hold on. Yeah, got the cursor. Okay, so this is the 1's place. This is 10's place, 100's place, thousands, 10,000s, and 100,000's place, right? And we call this the 100's place because that represents 400 right there, of course. And so what's going to happen in binary is that this is the 1's place, this is the 2's place, this is the 4's place, okay? So this is the 4's place, and here's the 8's place. And if I add, let's add some numbers. This was 8's place, so this will be 16, then 32, then 64, then 128. Do you see the pattern? I'm doubling each time, right? It was 2's place, 4's place, 8's place, 16th place. So doubling each time means that it is 2 to the something power, okay? This is 2 to the 0th power, which is 1. Anything to the 0th power is 1. This is 2 to the 1st power, 2 to the 2nd power, which is 4. So that's the 4th place. So if there's a 0 here, it's 0. It's always 0. But if there were 1 here, it adds 4 to the whole number. So let's calculate what this number is. So we're going to have 1 times 1 is the, okay. Then that's this number. It's just 1. 1 times 1 is 1. Here, this is the 2's place. So it's going to be 1 times 2 here. We're always adding the value of the digits. So this is the 4's place, right? 4, yeah, but it's 0, so we don't care. Just for demonstration, I'll write it out. Times 4 plus. Then we have, the next place is an 8th place, so 1 times 8. Do you see the pattern? So I'll just quickly write out the rest of it without explaining it with words. In case, wait, 16, we have then a 0. I hope I don't make a mistake here. Comment if I do. Times 64 plus 1 times 128. So if I remember correctly, this is 2 to the 6th power. Kind of easy to remember because there's a 6. This is 2 to the 7th power. 2 to the 8th power would be that. And let's see, 512 is it? And then 1024. So 2 to the 8th power, 2 to the 9th power, 2 to the 10th power. So 2 to the 10th power is kind of easy to remember because it has a 10. So this is 2 to the 10th power. So this is just like general math, useful stuff. That if somebody gives you says 2 to the 30th power, you know, approximately what is that? Well, you take 2 to the 10th. It'll be, this is going to be this times this, right? So it's approximately a billion, because if we approximate as 1,000, then this is approximately a million, and this is approximately a billion. So I can say rather quickly that 2 to the 30th power is about a billion. And if they give me 2 to the 32nd power, I can say that is roughly going to be about 4 billion or so. So if this is kind of useful to be able to do this in your head, you know, approximately when you're talking about bits and bytes, and you know how many bytes would be in a 32-bit number. This kind of arithmetic I've personally find useful. So, but anyway, that's not really what the video is about. But it's good to remember that 2 to the 10th is 1024. That's kind of easy to remember. Now you may have seen this 256 number come up in programming, and that is 2 to the 8th bits. 2 to the 8th. And just to recap, you know, so like here, this is a 8-bit number. For each item here, you have 2 possibilities, right? It's either a 1 or a 0. So if you've ever studied probability, you know, when you want to count the number of total possibilities, you take, well, okay, for this digit here, there's 2 possibilities. And then for the next digit, there's 2 possibilities, and so on. And you have to do this 8 times. I'm just going to kopipe, as we say in Japanese, kopipe. So, yeah, that's how many possibilities there are. So that is going to be 256. And that is, so we can store up to 256 values in an 8-bit number. And by the way, for whatever reason, 8-bit numbers are referred to as bytes. So this is a byte, okay? So I'm going to put that here. This is a byte. Now, let me just make sure it's recording. Good. All right. It's a byte. And what else? Anyway, so that's just a introduction, a little taste of it, right? And so it's good to know what binary is, and what bytes are and bits and all that stuff. And this is not even the first video. This is just an introduction. So I'm going to actually do all of this again in a more organized way in the first video and explain all kinds of things. But just for those who have no idea what binary is, this was a real crash course, little explanation. So if you want to understand how a computer works, it's really important that you know what binary is. Now, why does it do ones and zeros? Because at the base level, there's these things called transistors, and they act like switches, on and off. And we represent, you know, on as 1 and off as 0. And so the computer has lots of transistors, you know, millions and millions of transistors, and this is sort of the language that the computer speaks, how it works. And so it's not that you need to teach the computer binary. It's that the computer knows binary and it doesn't know anything about our normal decimal numbers. So if you were building a computer programming language from scratch, the computer doesn't know binary in the beginning. So, you know, if you were building things up from scratch, everything up from scratch, you would have to teach the computer system how decimal numbers work. Assuming you want to use decimal numbers, which if you want your computer to work well with humans, you know, humans are often using decimal numbers, the ordinary base 10 numbers, okay? So anyway, so that's a little introduction of this topic. But now I want to talk about sort of the deeper math stuff that I am interested in. And like I said, my series is going to be unique in that I'm going to be tying. So we're going to be looking at different bases. There's binary, obviously. We'll talk about hexadecimal, which is base 16. And that's just more useful because if you imagine you have a 64-bit number. It's 64 ones and zeros. It's very difficult to look at it and make any sense of it. So what we'll do is we'll represent it in hexadecimal base 16, because in base 16, for example, let's see. So 16 times 16 is 256, right? And so this 8-bit number gets represented as one number in hexadecimal. So in hexadecimal, 1 byte is one number. So if you had a 64-bit number, that is 8 bytes. right? 8 times 8 is 64, so 8 bytes. So in hexadecimal, it's represented as 8 numbers, okay? Whereas in binary, it's an array of, well, it's a list of 64 ones and zeros, ones or zeros, right? So it's much easier to deal with these 8 numbers in hexadecimal than it is with binary, right? So obviously we're going to discuss binary and hexadecimal. There's also sort of historically, sometimes base 8 was used. That's called octal, okay? And in roughly 10 years of programming, I've never really needed octal. However, it's good to know, personally I like to know how it's represented in a language if I learn a language. Mainly because, like, for example, if there's some kind of weird quiz about the language, or somebody is discussing the language in an online video, and they're saying, like, they're talking about the quirky things about the language, like, talking about the octal representation of numbers is a thing that might come up. If you're going to a job interview, they might expect that you know how octal numbers are represented in that language. Now, again, I've never really seen it used in the wild. I see hexadecimal is used and important, but octal not so much. But anyway, it might come up in a job interview. It might come up on these weird quizzes. Also, there's like code golf, which code golf is where you try to write code as compactly as possible with as few symbols or letters or numbers or whatever as possible. So that's code golf. So it would come up, there's all kinds of crazy techniques with code golf that might come up. Or code obfuscation. So if you're interested in cybersecurity, sometimes people will write code and they'll deliberately obfuscate it, meaning that they will make the code hard to understand on purpose. And so there you might have things octal being passed around, like you have numbers and then you keep like switching up the bases all the time, like throughout the code, the base of the numbers is being switched around. So it's extremely difficult to reason through the code. So you'd have to go in and you might want to like undo all that craziness, right? So with code obfuscation, it is also relevant, of course. Basically, if you're getting into code golf or code obfuscation or code minification, then anything that's possible in the language is of interest, basically, right? So anyway, octal, not that useful, but worth mentioning, worth knowing about. Yeah. So you might see like for example, in hexadecimal might be represented like this, where you have this is like a prefix, and then this is well, anyway, we'll explain it another time. And I think octal in some languages will be written like this kind of stuff. So you might have like 2, 5, for instance. The B, I think I kind of have to review it. It depends on the languages and all that stuff. Yeah, or maybe just a zero like normally you wouldn't write a number with a 0 in front, but in some languages this makes it into an octal number, I think. Okay, anyway. So the math stuff that I'm interested in. First of all, symmetries are hugely important in advanced mathematics. And basically, this is group theory. Okay, and if we talk about continuous groups, there are these things called Lie groups. Because now I say Lie theory, there's also these things called Lie algebras, which, so these are, we're talking about now about continuous groups. So there's continuous and discrete groups. So I haven't said what a group is yet. I have a past video where I think I talked about groups, fields, vector spaces, like all this. This is sort of abstract algebra, like what all these things are, roughly speaking. And so I may probably in one of the videos, if I talk about groups, I'll explain quickly what it is. Groups are interesting. Group theory is interesting. It is sort of confusing to get into because, well, you study these structures, and so mathematical structures where you always have a binary operation. So what is that? Well, you already know a bunch of binary operations, like multiplication and addition are binary operations. In this case, the binary just means 2. It means that you have, right, when you add stuff, you need 2 things. So these are binary operations. Actually, this comes up in computer science programming stuff. If you have, for example, increment is a unary. I'm not sure on how to pronounce it, but I think it's unary. What's another unary operation? So the input is just one number for an increment, right? You don't need 2 numbers. Increment, decrement. Can you think of other examples of unary operation? I mean, you can kind of take, like, for example, multiply by 5, for instance, right? You can, if that's your operation, you can think of that as unary. So, but anyway, so it just takes one input. Binary operations take 2 inputs, right? So in group theory, you have always a binary operation as part of the group. It starts with a set, so a set of numbers. It could be all the. It could be an infinite. If it's an infinite group, you could have all the integers, for example. You could have just the numbers 1, -1. Actually, that's enough. That you can form a group with those under. This forms a group under multiplication. Right, the multiplication table. Let's see if I can do this on the fly. We'll have, these are the elements of the group, and then, so 1 times 1 is 1, this will be -1, this will be -1, and then this will be 1. I believe this is a group. So it needs an identity. Every element needs an inverse. So since I'm already doing this, we're basically defining a group at this point. A group is a set with a binary operation. A group is a set with a binary operation with the following 4 properties. We have the identity. Okay, the identity here is 1. Here the set is these 2 numbers. The operation is multiplication. I'll just write multiplication. So we have identity. We need all elements. So this is elements of the set. Have inverses. And then we have a couple more requirements. One of them is associativity. Okay. So that's like, element 1 times element 2. Element 1 times element 2 times element 3. This kind of thing. A lot of you have seen this before, so. Oops. Times element 3. Let's put a times symbol here. So, and then the other requirement is closure, which means that you don't multiply something and then get something outside of the set. Every time so think of this binary operation like a machine. It takes 2 inputs and spits out 1 output, okay? every time you take two elements of the set and shove it into the machine, you get out another element of the set. It doesn't spit something out that wasn't in the set. Okay, that's closure. So if you have if you have a set with a binary operation and it satisfies these four properties, you have a group. Now, why do we have this definition? Like, for example, we could talk about where you don't have inverses or you don't have an identity, and I'll speak about that in a second. But anyway, we have this particular definition because it's very interesting mathematically. There's groups come up throughout higher mathematics. And you're familiar with a bunch of groups already. If you want a little exercise, add to this group, add the imaginary number I, that is the square root of -1, and also negative I. And then write out the multiplication table and try to sort of prove all of these four conditions. Okay. If you're not familiar with I, the square root of -1, forget about it. But I think this is a fun little exercise. And see if you can think of any other groups. So that's a group. So you could, so definitely mathematicians study this a lot. It's called group theory. It's usually part of abstract algebra. So a lot of people in STEM who study STEM in college will take an abstract algebra course. It's definitely required. If you're a mathematics major, you'd better study group theory for sure. Now, we could, for example, relax some of these requirements. We can get rid of this one, for instance. And then we have what's called a monoid. Okay, so a monoid is a group, roughly speaking, it's a group without the inverses requirement. Okay. If you also scratch out identity, apparently it's called a semigroup. So there's also a semigroup where you do not have these two requirements. I'm not sure about the associativity. If you're curious, you can look up semigroup. But I've never even done anything with a semigroup ever. And up until just a couple days ago, I'd never done anything with a monoid either. But monoid is a word that comes up in category theory a lot. And category theory is like, if you go deeper into programming, sort of really advanced concepts in programming, category theory could be useful, could be interesting. It's often related with related to functional programming. So let's functional programming like Haskell, Scala, etc. Okay, so by the way, functional programming, I see some people in like the Roblox community and stuff like this, they think that functional programming means that you have functions. And that is an extremely useless definition because almost all programming languages these days have functions. Okay, so functional programming doesn't mean that something has functions. I've seen this mistake made at least a couple times. Functional programming, basically the ideal here is that, so for those who don't know, a function is basically a block of code. They used to be goto statements where the code execution will just move to another spot in the code. But goto statements have some problems. It becomes difficult to reason about the control flow in the program when you have a lot of when you get complicated code with a lot of goto statements. It becomes very difficult to reason about. So they evolved into functions, and it's just a block of code. Okay, usually represented like this, or some people, it's a matter of taste, might put the curly braces down here, and then we just have a bunch of code. Okay, down in here. So it's basically a block of code. Now in functional programming, what they do is, the ideal here is to not have side effects, which means side effects are when something in this bunch of code affects a variable that is outside of this function. So the ideal in functional programming is you have some inputs. So we'll say input A and input B, for example, and we could have lots and lots of inputs, whatever. And usually there's some kind of return statement. So for example, let's say a plus b, for example, this function now just adds two numbers, right? So this has no side effects right now. It's not like if we had some other variable up here. So let's say an integer, an int x equals 7. Okay, well, this is not affected here. But if I said x equals 3 right here, then this is a side effect. I'm affecting this code. We said, or this variable. We said that this variable is outside the scope of this function. I could have said like, oh, this is a global variable, but all of this could be inside some other thing where this is not necessarily a global variable. Here it just has scope that is outside of the function. So this is a side effect when you're affecting some variable that is outside the function. And so it's a side effect. And side effects can also they can be surprising sometimes. Like, so let's say your function is 100 lines of code, which is not unusual. That's kind of big, but I'd say it's not unusual for a enterprise production level code base, So if your function has a lot of side effects, it starts affecting variables that are defined in other files in the code. It can become surprising to work with, unwieldy. Like, it means that you really need to understand exactly what this function is doing every time you call it. And kind of the idea of, well, it's a common idea that we would like for our functions. Sometimes we want things where you can kind of look at the name of something, understand what it does, and then you don't need to really know the details of how it's implemented, right? That's kind of an ideal. This is sort of, we talk about abstractions, right? So maybe you're at a company and the tech lead understands the entire code base, how everything works, how everything is implemented, and every time that person does anything, they are very aware mentally of all the side effects of of those functions and code and all that stuff. Fantastic. But not everyone in working on the code base is probably going to have that level of expertise, and even the tech lead probably that's a fantasy. So anyway, so this idea of getting rid of side effects is a potentially noble idea, okay? But for example, the reason that, so often Haskell is sort of called useless. In fact, the creator of Haskell kind of called it useless, okay? Because if you have some user input and then user output, basically you want to, or let's say some kind of output like graphics or something, for example. You want your function maybe to mess with some of the output, the graphics, right? Something on the screen. Sometimes you want your functions to really do stuff that affects outside of the function. That happens. And so this ideal is not going to be great for that. So what they do is they have anything that affects these outside things, okay? Like anything that's actually going to output something, for example, is in its own special category. And I think, do they call it monads? So, see, like I'm not experienced with functional programming. I just kind of know about it. But anyway, so it is a good idea, useful, interesting idea that anything that would have side effects or sort of like affect output that these are often their own, they're kind of separated from the rest of your code. Like that's kind of the functional programming paradigm, okay? So that's the idea. So that you separate your code into, oh, here's stuff that are pure functions, which means a pure function has no side effects, okay? And then, so you'll have, your code is divided into these two areas. You have all your pure functions over here, and then you have like your dangerous side effecty thing code over in this other area. And so the idea behind that is when you look at your pure functions, you can reason about them more easily. And in fact, these are useful also, I think, for like proving things in computer science. So you can, when you have a bunch of pure functions, I think you can like prove a lot of things about them. Whereas if you had, imagine if you had a function that had a lot of side effects, like you can't look only at that function and prove something. Because you have side effects, you would have to look at what those side effects are, right? You'd have to look outside of the function in order to reason about things. So pure functions are useful for proving things. For example, proving the safety of things. If you're like, there's all kinds of programming in, I think it's called mission critical programming. For example, medical devices, stuff that works with heavy machinery that could be dangerous. Say like equipment for air traffic controllers or airplanes or cars. You know, nowadays there's a lot of code involved with all that stuff. So you have a lot of mission critical situations where failure could mean injury or death to humans. And being able to prove that something is safe, or to, you know, clearly see that something doesn't have side effects is of interest. Now, a lot of those mission critical things that I just mentioned, a lot of that's generally called embedded programming, embedded systems. So if you're talking about like an airplane or the chip in your, if your washing machine has a chip in it, or even like a teddy bear, maybe has, you know, you poke it and it reacts or whatever. So it has a computer chip in there. That's embedded programming. And this is usually done with quite limited memory and hold on. So you have quite limited memory, so usually the C programming language is used. Sometimes even assembly might be used. Assembly is basically can be directly translated into machine code, which is what the computer understands. So, but C has a lot of issues, and people are trying to move towards Rust. I've studied Rust a bit. Problem is, Rust is very complicated. The learning curve is very steep, and it's not just me. A lot of people are criticizing this. That somebody I was watching recently said Rust has been trying to please too many people, and they're trying to get kind of all the functionality that you would have with C++, more or less. And so the result is that the language is very complicated. And I've learned a lot of programming languages, and I'll say that Rust is by far the most difficult thing I've tried to learn so far, and I have not learned it. I've spent, I don't know, 30 hours, and I'm still confused. So Rust is very hard to learn, so just watch out for that. All right, so we talked about a lot of different things here. Let's get back to the math. And I'm realizing like this could be like 10 different videos, you know, branching off into more detail of what I'm talking about. But those would be separate playlists probably. Kind of went on a tangent about functional programming. But and Scala is probably more useful than Haskell. I've met someone who does Scala web development, and it sounds interesting, but you have to, for example, if you have a function that has no side effects, like, okay, sorry, I'm going on more of a tangent, but you have, let's say you have some reference to a bunch of data. So by reference, it could mean a pointer or objects in languages are usually, they're just pointers to stuff. So a pointer is like what it sounds like. So for example, in the C programming language, it literally represents an address in memory. So pointer, literally it's a number, but it's it's just data. It's just ones and zeros, right? It's just a number, but it is interpreted as a address in memory. Okay, so a pointer points to things. And so objects are usually pointers to, it might be data. Well, the idea of an object is that it can contain different things. So it might contain data, it might contain functions and stuff like that. So, yeah. Anyway, so you have some reference to, like, let's say you're working with a large amount of data. It makes a lot of sense that you would, let's say you want to call some function that manipulates the data. Again, it could be graphics, for example. In graphics, in low-level graphics, you have buffers. Okay, buffers are just a bunch of data. And so when you're going to display something on the screen, you have a screen buffer, which contains, it's supposed to contain all of the data for displaying stuff on the screen. Well, it could just be a window, right? Not necessarily the whole screen. But if your window is full screen, then it would be the whole screen. So you have something called a screen buffer. So it makes sense that you might want to point. So for example, if you have a frag shader or a fragment shader, for example, you're pointing, like let's say you have a specific triangle on the screen. The idea is, I'm just being kind of vague and hand wavy, but I'm thinking like, you might have a pointer that is pointing to some data and you're using a fragment shader to manipulate that data. Something like that, right? So it's because these screens these days have a lot of pixels, right? So we're talking about a lot of data. So it's very natural that you have some function, you want to manipulate some of the data in the function, some of that external data in this function. So it would be bonkers, it would be totally crazy to copy all the data every time you do this into the function and then manipulate it and then output it, right? Copying a lot of data, like let's say your full HD, which is 1080p, right? So that's 1920 by 1080. Okay, roughly speaking, this is roughly 2,000 times 1,000, which is roughly 2 million. Right? So 2 million pixels on the screen. So if we have, let's say, color is usually, so basic, let's say just basic color is 3 bytes. We have a red, a green, and a blue. This ties back, the origins of this basically is the human eye. It was discovered at some point, I think like 150 years ago or something, that your eye really is just detecting red, green, and blue. There are some people who have a fourth type of cone, and can see a little bit of color. I think it's like 1% of the population has 4 types of cones, and they can see a little bit more towards the blue end of the spectrum, right? Like light is a spectrum that goes, so light itself is basically on a one-dimensional line. It's just a line, right? Like lower energy, the light spectrum, like, it's ridiculous how I go from like talking about binary and now we're talking about the light spectrum. But anyway, right? Think of a one-dimensional line, and we're graphing the frequency of the light. So lower frequency is, we often call radio waves, etc. And then it goes to infrared. Infrared means a little less than red. Then we have the visual part of the spectrum, right? And then we get into ultraviolet, UV. And UV, I think there's very limited cases in physics, maybe older texts, where UV, I've seen it, I think, once or twice, where it was meant to be everything of higher frequency than blue. So everything ultra, meaning more than, or extreme, than violet, right? So, and I think I've even seen, like, in some cases where infrared just meant everything less than red. So, I mean, that's a useful thing in certain contexts to say there's the visual part of the spectrum, then there's everything less than red, and there's everything greater than blue. But we have all these labels like radio waves, microwaves, X-rays. At the far end of high frequency, we have gamma rays. And these are just labels. It's just a single number, right? There's photons. Photons have frequencies. So I remember in my science education, K through 12, I was left actually quite confused about all these different types of light. You know, all light is just photons, and an individual, well, the quantum mechanical details are complicated. Classically speaking, you can think of a photon as having a specific frequency. In a lot of contexts, yeah, it has one frequency. But anyway, RGB, so this has to do with how, so some people have 4 cones. They can see a little bit, I don't know if they can see a little bit into ultraviolet, but these very high frequency colors will start to look different for them than what it is for the rest of us. So normally, anyway, 99-ish% of the population, we see RGB. We have 3 types of cones in our eyes. And these, and color, all color for us, are linear combinations of RGB. Most people is linear combinations of RGB. Linear combination is some amount of red. So this is a scalar multiplier. In other words, it's an ordinary number times red, some amount of red, plus some amount of green, plus some amount of blue. Okay? Linear combinations. I've talked about this in previous videos on the channel. It's a simple idea, really, but this is a 3-dimensional vector space now. But what's weird about color, so you can have this sort of cube of color where at the origin at 0, 0, 0 is black, and with maximum red, green, and blue, you have white. So this sort of forms a cube, but it's kind of weird because, well, I won't get into the details. But wouldn't it be interesting, like, if you had a different system where, for example, you could have like red times red? Red times red is sort of nonsensical. So, but I'm imagining like a higher dimensional object where there's like a red pole and a green pole and a blue pole, right? And maybe you would need the same for these cyan, magenta, and yellow. So if we combine red plus blue, we can combine these 3 different ways, right? Red plus green, we can do blue plus green. I'll write it green plus blue. It forms a triangle, right? Imagine 3 vertices of the triangle at RGB. How many different ways can you connect these? There's 3 edges of the triangle. It's also 3 choose 2 if you know combinatorics. Wait, 3 choose 2 would be 6. No, wait, what? No, it's 3. It's 3. My brain had a bug. This is, anyway, I'm not going to do the math of the combinatorics. Anyway, there's 3 ways to combine them. If you combine, let's see what I can remember here. Red plus blue, I think, is going to be magenta. Green plus blue is going to be yellow. And I'm pretty sure I got something wrong here. This is cyan. This is yellow. So it's different. I hope I didn't make a mistake. But it's different if you're talking about, there's two color schemes. There's additive and there's subtractive. If you're talking about paint, it's subtractive. When you add two types of paint, if you took lots of different colors of paint and you just added all of them together, you get black. Because how paint works, how normal things work, normal like physical things, is that the color that you see is the color that's being reflected. So it's sort of the opposite of the color that's being absorbed, right? So if you mix all these different colors together, what happens is they absorb a very large amount of different colors. So if you take it to the extreme, and if they absorb all the different possible colors in the visible spectrum, well, if they totally absorb red, green, and blue, then they reflect basically no color, which is black, the absence of color. Okay. Now these red, green, and blue, I'm not going to talk about that. There's a lot of stuff to talk about, but so you can think of cyan as sort of being anti-red, the opposite of red. Wouldn't it be interesting to have a higher dimensional object where you can multiply colors and you have sort of poles, just like you have North Pole and South Pole. You can only go so far north. Once you reach the pole, if you're at the North Pole and somebody tells you go north, it's like a nonsensical instruction, right? So I spend some time trying to imagine a higher dimensional object that contains color. Because the vector space analogy here breaks down. Because you can't keep adding red, green, and blue forever. The vector space, analogy sort of breaks down here. But anyway, that's how most people think of color, as just a cube, RGB. What the heck was I talking about? I was talking about fragment shaders, but good lord. So, so it makes sense that you often want to edit some amount of code here, and then that is a side effect. So, sorry, you want to take in some kind of reference, okay? So like pointer, let's say pointer to graphics, okay? You take it in as input, and so this is of type pointer. We called it PTRG. So it's a pointer to some graphics. And it makes sense that you would want to manipulate it. I mean, it's a very common, side effects are something that you very commonly want. You want to manipulate some data that is external to the function, right? So this discussion that I talked about of functional programming, like you might have heard that and thought, oh yeah, side effects, we don't want those. This makes sense. Pure functions. Let me do functional programming. Sounds great. But I'm saying, no, you very often want side effects. You often take in some kind of reference or pointer, some kind of reference to data. It could be, in a different language, it would be an object, okay? You take it in, this reference, and you want to manipulate the data in that reference is pointing to. That is a very common thing that you're going to want to do. So if you're new to programming, do not dive into all this functional programming stuff. This is much more advanced stuff. Avoid it for at least a couple of years, okay? Now, so it's a very common thing that you actually want side effects. But what something like Scala might do, if it's trying to force this to be a pure function, it will instead take all this data and make a copy of the data, okay? So that's this sort of hack to get your functions to be pure functions, to avoid side effects. You copy all of the data, you do a bunch of stuff, and then you return it. And now it's not a side effect. Now you're just returning this data that you've manipulated. So great, it's not a side effect. But if you had to copy all of the data for the screen, for example, we have 3 bytes per pixel. It was 2 million pixels. So that's going to be 6 million-ish bytes. Okay. And if you have a game that is running 60 frames per second, and so that's, let's say you're manipulating each byte once. Okay. So 360 million manipulations per second. Let's say this is your function or whatever. So you see that this is a lot of manipulations per second if we're talking about graphics. And if you're copying a bunch of memory, like if you're doing this every frame, that you're shooting yourself in the foot. That's just a total no-no. You just can't do that here. So when you're dealing with a lot of data, this idea that you're going to always copy the data, manipulate it, and then return it is it's a really bad idea if you have a lot of data. If you're just talking about a few bytes, okay, fine, that's cool. Like I'll take that for the convenience, sort of the mental convenience of this pure function thing, where you have this ability to reason about things where, well, if you have a lot of pure functions, you don't have side effects, so it can be easier to reason about things. That's great. And if I'm just dealing with small amounts of data, fantastic. I'm for it. However, that's often not the real world. So this question, so I've never actually done any Scala. I've just talked about, a friend of mine does Scala, so we've just had conversations sometimes. So from what he told me, it sounds like functions cannot take references and then manipulate external data. They always have to copy the entire, like if you send it an array, a big array of data, it will copy it and then manipulate it and then return the data, which is expensive. That's computationally expensive. So, but I think there's a way to get around this, but you just have to use this other thing, and it separates the, kind of separates, like I was saying before, you separate your pure functions into some other thing, and then you have, I don't know what they're called, monads or something somewhere else that are different, and it separates it. And so actually that is interesting. I do want to learn Scala and maybe Haskell. It is of interest, but for some reason I got into a big discussion about that. Okay. So binary operations, let's get back to the math. Group theory, we have continuous and discrete groups. These continuous groups are basically called Lie groups. I think there's some kind of distinction, but it's not really important. We also have these things called Lie algebras. So altogether, I call it Lie theory. There's almost a one-to-one correspondence of groups and algebras, but it's not exactly one-to-one. There's more to talk about there. It's a little complicated. And this whole business of Lie theory, I have some videos up about it, but it is complicated. It is not easy. It is graduate level mathematics. I still haven't come across, when I talk to people who have graduated, they have a degree, a bachelor's degree in mathematics, they never understand. I talk about Lie groups and they've never even heard of it. So it's unfortunate, but it is complicated. So if we're talking about symmetry and continuous symmetries in particular, because discrete symmetry, there's this effort to classify all discrete groups, and they've kind of done it, but it's like 10,000 pages long. So it's a big, complicated thing to classify discrete groups. Now, with continuous groups, there's some kind of distinction about, like, they call it simple groups or semi-simple groups or something. And I think there's one that's way too complicated. You can't possibly classify, but then there's this other stuff like this. I forget exactly, like the semi-simple continuous groups or something that is classified. So the Lie groups are classified. And it's actually not that long of a list. There's like, I think there's like 9 different things. 9 different classification. I want to call them categories, but there's 9 different types. Okay, so that's cool. This is hard to study. I studied this a lot. It took me a long time to make sense of it. I kind of understand it. It's actually amazing and cool. I love Lie theory. It's probably my favorite math. There's a whole different way of looking at this symmetry. And by the way, we're talking about all kinds of possible symmetries in any number of dimensions. So it's a deep subject to study. It's very important for particle physics and unification physics. So all of particle physics, which is sometimes called the standard model of particle physics, and basically what I mean by that, everything that isn't gravity in modern physics. There's just particle physics and gravity. You could also just call this quantum physics or quantum field theory. So all of this is basically can be described with 3 Lie groups. We say U1 cross SU2 cross SU3. Just 3 Lie groups, more or less, can explain all of particle physics. So all of physics except gravity, more or less. Which is amazing. And so that was a big motivation for me to study Lie theory. And this one you're familiar with. This is the symmetry of a circle. This one is basically the symmetry of quaternions. So if you're doing any kind of game development, quaternions do come up. They are at first at least, they're extremely confusing and hard to understand. And don't feel lonely in that regard, because even for decades after quaternions came around, even the greatest physicists of the time were struggling with quaternions. But anyway, SU2 is roughly the symmetry of the quaternion, or at least a unit quaternion algebra. Unit quaternion just meaning that they are of magnitude 1. And so when we get to SU3, this is... And by the way, if you've heard of spinors, this is the same thing. So they're not... This is all not exactly the same thing, but they're what we say is isomorphic, meaning you can sort of, in a one-to-one way, map everything from one of the things to the other thing. So there is a one-to-one mapping of unit quaternions to elements of SU2. And actually, there's a whole bunch of isomorphisms here. So we have spinors, specifically elements of spin 3. And there's a bunch of other things. So there's this thing called Mobius transformations, which are super interesting. There's also SU2. There's also the Lorentz group, which is used for special relativity. So these are... I'll write down SU2 here. All of these are, I'll say, unit quaternions. All of these are different things, but there are one-to-one mappings between them so that they're all isomorphic. So basically, if you were in some situation where you're thinking about quaternions, you could switch to thinking about spinors or Mobius transformations or Lorentz groups. The Lorentz group. So that's really interesting. There's this thing that comes up in many different places in physics and math. This SU2 structure, or you could call it a quaternion structure, whatever you want to call it, right? It comes up in many places. Very interesting. And this is already very complicated to understand, okay, all of this. But then you get to SU3. SU3 is really hard to understand. I mean, you can kind of just understand it in quotation marks in terms of its definition and stuff. Oh, yeah, it's the matrices that satisfy these conditions. But you don't really... That's not an intuitive understanding of anything physical, in my opinion. So in the same way that I've really studied the heck out of all of this stuff and gained a lot of intuition, although I still need to do more work on that, in that same way, I set out to understand SU3. And it's very, very hard. This is the symmetry structure of the strong force. So all the stuff with quarks, gluons, the strong nuclear force, that's what holds the nucleus of the atom together. And that the reason, well, it's called the strong force because it's very strong. And that is when a nuclear bomb goes off, that enormous amount of energy that's released is because of the strong force. It's because the strong force is strong that there's an enormous amount of energy released in a nuclear bomb, and there's a lot of energy that we can get from nuclear energy. Okay? So I think you need basically 2 copies of this. So the SU2 is related to the weak nuclear force, but it's also has everything to do with the spin in quantum mechanics, which is often called 1/2 spin, which for mathematicians is confusing. Like, what are they talking about? And then you explain to them what it is mathematically, and they're like, oh, it's this is basically it's basically the space of transformations, which is basically transformations of a 2 complex dimensional vector space. So I've talked about vector spaces on this channel, but I've talked about real vector spaces. So you can also have complex dimensional. And so the elements, so you have some vector. I'd like to write it as column, but I don't see how I can do that. Let's forget the brackets. You just have some A and B. Pretend this is a vec2 or a 2 vector, right? It's a vector with two elements. Is elements the right word? 2 components, I guess. 2 entries. I don't know. Anyway. Or we'd often say X and Y, right? And we're often talking about like a 2-dimensional game, for instance. That's a 2 real dimensional vector space. Well, you can talk about, well, what if these are complex numbers? And you can have a complex dimensional vector space. And so this whole spin 1/2 business, when people talk about the spin of an electron, and it works for all the fermions, all the matter particles, which is electrons, quarks, and neutrinos, they have 1/2, what they call 1/2 spin. It's kind of a silly name, but it's for historical reasons. The history is the Stern-Gerlach experiment, if you're interested in the spin of electrons. And I believe it's because the result they were getting was 1/2, something about Planck's constant and 1/2. So it's for historical reasons. So, but if you have a mathematician and they're starting to learn about this stuff, it sounds confusing. 1/2 spin, what's that? But it's basically the transformations of a 2-dimensional vector space, which is what Mobius transformations are basically about. Actually, I should say, yeah, I think this is okay. I was trying to get confused in my head. Because you can... Mobius transformations are really about... you can think of them as transformations, yeah, of a 2-dimensional vector space. Yeah. But there's a way to think about this as just, you have a complex plane, which is one... usually when we think about this, we think of one complex variable, which is we represent in the complex plane, and then we sort of do transformations on that plane. And the reason we do that is because we can't think in 4 dimensions, which you would need to think. You would need to be able to do to think about this, because it's 2 complex dimensional is 4 real dimensions. And all of this stuff is basically 4 dimensions in terms of real dimensions, right? Normal dimensions. The quaternions are 4-dimensional, Mobius transformations, SU2, the Lorentz group, and special relativity. All of this is basically kind of working in 4-dimensional, 4 real dimensional vector space. Okay. So anyway, so yeah, this SU3 stuff, really confusing to think about if you're trying to understand it in any kind of physical, intuitive way. The strong force, textbooks on strong force are very difficult, very confusing. But anyway, I've thought a ton about this stuff, and I do have some interesting things that I would say might be insights into understanding it. But anyway, it's for a topic for another time. So the fact that it's just, well, anyway, it's 3 Lie groups. So that's amazing. And then, so all of physics as we know it is 3 Lie groups plus gravity. So let's do this. All of physics as we know it. Can't type. Plus, we need gravity. But somehow these are interacting, gravity and quantum physics. And so, you know, if we're talking about the surface of black holes, both of these become super important because the gravity is extreme. But right on the surface of a black hole, we're talking about like a very small area. Can kind of, at least theoretically in our minds, we kind of zoom in right at the surface and try to think about what's happening. And, you know, quantum physics is going to be really important. It's kind of a myth that quantum physics is only about the really small. I mean, a photon traveling from the sun to here, it travels a great distance. And yeah, okay, photon is small. But see, like, as far as we know, quantum physics applies just as much to macroscopic big objects as it does to small ones. So yeah, I'll say it again. It's kind of a myth that quantum physics only applies to things that are small. Okay. So this is kind of physics and stuff that I'm interested in. And so symmetry, the study of symmetry is sort of the central theme, really, in all of this stuff. It sort of starts with group theory and discrete groups. It goes to continuous groups, which are generally basically Lie groups, Lie theory, and all of this stuff. And there's a whole other way of approaching the study of symmetry, which is Coxeter systems. And that is where, so it's named after this mathematician named Coxeter. He's a relatively recent mathematician. He died, I think, like 2004 or something like that. And there used to not be so many good videos on YouTube about Coxeter stuff, but I would highly recommend if you want to learn about Coxeter systems, this channel, Joseph Newton. This guy has 10 videos and 44K subscribers, pretty amazing. And talking about the Suica game here as well. So I've watched probably all his videos, good stuff. But anyway, it talks about Coxeter systems. This is, I think, the only, I haven't watched this, but 246 views. It's basically the only videos on YouTube about Coxeter systems that are meant for the wide public, like the research level mathematician public. And so there's 2 versions of this whole discussion. In the second one, he talks about representation theory, which is where we use matrices to represent groups generally. So yeah, it's using matrices and linear algebra. And before that, the first video is meant for a wider audience, not maybe including people who don't understand about matrices and linear algebra. And so that's this one. But it's actually a little... so if you're an expert in linear algebra, then this is actually easier content, basically. If you're past that hurdle, it's sort of easier to use representation theory, to use matrices, because they're kind of powerful. The combinatorics side of things is actually harder to understand, sort of fundamentally speaking. But so Coxeter systems, it's basically looking at the geometry of things, like, for example, polyhedra, so like cubes, octahedrons, dodecahedrons, icosahedrons, these kinds of things, tetrahedrons. And then, but in the n-dimensional case, and looking at other things, 4 dimensions sometimes is special. You have certain special objects. There's a 24 cell, which is extremely interesting. And so, yeah, in 4 dimensions, I'll talk about this more in the future, but 4 dimensions is very special. Maybe that's why we live in 4 dimensions. We have 3 dimensions of space and 1 of time. Might have to do with some of the special stuff that happens in 4 dimensions. And in particular, this 24 cell, very, very, very interesting to me. It has F4 symmetry, which is so this F4 has to do with the Lie groups and Lie algebras discussion. It's a simpler sort of predecessor. What would I call it? It's not a simple version. Well, I'll write this and then I'll fix it. Of E6, E7, and E8. You may have heard there's this crazy stuff about particle physics and E8, or really unification physics in E8. And F4 is similar, or sorry, simpler. And this 24 cell thing, polytope. So a polytope, polyhedra is in 3 dimensions, polytope is n dimensions. So if we're talking about 4 dimensions, we need to say polytope. And it has very special symmetry. And so if you take this F4 symmetry, which has to do with the 24 cell, and if you basically take all the vertices, or I think it might be better to think of it in terms of a lattice or something. But if you take these vertices and then you sort of complexify them, so instead of a real number, it's now a complex number, then it becomes E6. And if you sort of quaternionify it, you get E7, and if you octonionify it, you get E8. I think that explanation is correct. So this is extremely interesting. F4 is very important for other reasons as well. Anyway, so the Coxeter system is a more geometric, sort of a more intuitive way of looking at all this continuous group, Lie theories kind of stuff. And then there's lattices, which is kind of what it sounds like. Like a grid is a lattice. If you're tiling, like a square tiling, for instance, or these are examples. So rectangular tiling, you have in 2 dimensions, there's hexagonal tiling, which, so you can take a hexagonal tiling and sort of decompose it into triangles, So these are examples of lattices in 2 dimensions. You can go into 3 dimensions. Becomes very important in the study of chemistry, actually. But then we can talk about n dimensions. So the study of symmetries of lattices, okay, is also intimately... These are all connected. These sort of 3 versions of looking at this symmetry stuff. There's the Lie theory stuff, there's Coxeter systems, and there's lattices. And I'm weakest with lattices, and I'm currently studying those more. But these are E6, E7, E8 are both Lie groups, and F4 as well. They're both Lie groups, and they're also lattices. So there's a ton of overlap. But the overlap between these three ways of looking at things, it's not always one-to-one. Okay, so it's another thing. After you've learned all these three things, then you have to study the ways in which they're related in order to really kind of become good with this stuff. So it's very, very deep, complicated stuff. And how does all of this relate back to ones and zeros and different bases and ways of counting? Well, I've been interested in this idea. Gosh, this is getting so long. I'm not sure if I should. Yeah, we're at 1 hour and 20 minutes. So I'm going to talk about there's some way in which all this study of symmetry may connect back to doing different kinds of mathematics and different bases. And I'm also very curious if it connects with these things called p-adic numbers you may have heard of, or l-adic numbers. But we'll have to talk about that in the future. As you can see, there's these, well, I haven't demonstrated any connection with, here's base 7, because I was talking about, I'm interested in this very specific thing related to 3-bit numbers. If you have a 3-bit number, there's 8 possibilities, right? And so 0 through 7. And I'm sort of interested in stuff that sort of maps between this 3-bit numbers and octonions, okay, which I haven't even talked about. There are these things called octonions. They are the extension of quaternions, basically. So there's this thing called RCHO, which is real numbers. And then there's complex numbers, that's the C. And then there's quaternions, which are the H, named after, it's an H because Hamilton was the person who discovered them. Actually, there were hints of it before Hamilton, or like certain discoveries related. But anyway, kind of name it after him. And the fourth thing is octonions, and these are actually special. They're the only normed division algebras. So yeah, these 4 are special, and so there's these things called octonions. It's like, so quaternions in some sense are a generalization of complex numbers. They were partly discovered because Hamilton was looking for a 3-dimensional analog of the complex numbers, because complex numbers are very good for they're a nice, neat, useful mathematical package for when you have scaling and rotation in 2 dimensions. And we often sort of package complex numbers into that neat little package. And we think of it that way. So he was looking for a 3-dimensional analog of that because he wanted to use it in his study of physics, electromagnetism, and that kind of stuff. And although at the time they didn't have the word electromagnetism. Anyway, quaternions, so he came up with quaternions, but he found that they're 4-dimensional. So that was interesting. So the pattern is it goes from 1 dimension to 2 dimensions to 4 dimensions to 8 dimensions. So it's doubling each time. So anyway, an octonion, so then, yeah, I won't get into all the history right now. Octonions were discovered, and they have, you need 8 parameters to specify an octonion. They have, they're sort of in some sense 8-dimensional. So with a 3-bit number, you could represent, you could represent these integral octonions, which are so for example, with the complex numbers, you have Gaussian integers, which are basically in the complex plane all of the whole numbers, sort of. You can kind of think of it like that. Right, if the complex plane is a grid, okay, for example, you have 1 plus I. For instance, you could have 4 plus 3i, right, as an example. These are examples of Gaussian integers. You can kind of have the same kind of thing with integral octonions, which I'm interested in representing as 3-bit number. Let's say a vector space of 3-bit numbers, question mark. Okay, so adding together 3-bit numbers to represent integral octonions. So yeah, I'm gonna leave it at that. This is the madness that I'm interested in. And it doesn't make any sense to do what I'm doing, which is to like teach basics of binary and different bases while like tying it to much deeper mathematics. However, I don't think anyone else is doing that. So that's what I'm going to do, because it's the unique contribution that I might be able to make. Yeah, it's madness. I was going to I don't know. I was planning to just talk and like mindlessly explore things as I talk, but I ended up just doing everything in Sublime Text. So I'll have to do this kind of stuff some other time. Look at that beauty right there. Anyway, have a good day. Thank you and goodbye.